Well, I'd like to welcome everyone to the session on theories of consciousness. We're going to have to get started on time because we've got a very packed agenda, and we're going to have to limit our talks to 15 minutes, and we'll hold all questions till the end of the session where we can have everybody gather together to answer questions. I'm Bruce McIver. I'm a neurophysiologist, and so I have no idea about theories of consciousness. I don't even have many theories of the brain, but that's ideal because I'm not biased in any way at all. Right, Stuart? Yeah, I'm in the middle. So let's get started with Amber Hopkins from UCLA, and we'll move it along, and I will be ruthless, Amber. 15 minutes. Actually, if you do the math, it's 17. Right.
Okay, so hello everyone. Thank you for those that are attending. Again, my name is Amber Hopkins. I'm currently a first-year PhD student in the psychology department at UCLA, so University of California, Los Angeles. But today I'll be presenting work that I did at my undergraduate alma mater and where I was a post-baccalaureate researcher in neuroscience, Chapman University, which is in Southern California as well. And this is work with Dr. Kelvin McQueen, who is a part of the philosophy department there. And yeah, so if in this brief description of the project you don't get enough information, it has been published in Consciousness and Cognition, so you're welcome to wander over there and get more information if you'd like. So in this talk, I'm just going to go over three broad areas of the project. The first is kind of the philosophical motivation of the project, and I'm going to discuss just very little on testing theories of consciousness in general and progress there, and then go into our specific project, which we call filled non-filled pairs, and then finally how these challenge integrated information theory or might challenge integrated information theory. So to understand the philosophical motivation of this project, I wanted to bring us back to some basic and relevant philosophy of science principles. This project was kind of rooted in the desire to do some a priori testing of critical predictions of a theory. So we wanted to start with a theory, derive a critical prediction of that theory, and then conduct an empirical test. And the science of consciousness is very new, and this isn't my work. This has come out since my work has been published, but this is work by Itai Yaron and Liad Mudrik from Tel Aviv University. And I just think it's interesting to kind of put my project into context with what's happening in general in the field of theories of consciousness and research that mentions theories of consciousness. So this figure shows the distribution of experiments that did not challenge any theory, divided into theory-driven, so explicitly testing one prediction of at least one theory, the dark gray inner circle, mentioning, which just mentions some theory in the introduction, and then post hoc, which is the bulk of research that even mentions theories of consciousness in the field right now. And in this research, they interpret their results in light of at least one theory without referring to it in the introduction. So it's kind of conducting the experiment and then saying, where does this fit into theories? So our research, the goal was to be theory-driven, to kind of do this a priori prediction testing. So we started with IIT, and a few people will be presenting on IIT here, but it started with phenomenology, so reflecting on the essential features of consciousness, and it ends with a mathematical measure of amount of consciousness in a system, so the intrinsic integrated information, or phi. So for IIT, consciousness just is integrated information distributed across the brain. And the core prediction, or the prediction of IIT that we're focused on here, is that if there is a difference in phi between two brain states, then there is a difference in the experiences that the brain states determine. So to put that prediction into pictures, your experience of the picture on the left is identical to the experience in the picture of the right, and thus they must have, according to IIT, identical neural bases, so identical brain states with identical phi. Consequently, two brain states with different phi must correspond to two distinct conscious experiences, and two brain states with different phi cannot be related to the same conscious experience, cannot determine the same conscious experience. So we wanted to test this prediction and kind of design an empirical test for whether brain states with different phi can determine identical experiences. So what identical means here is important in the sense that we're defining identical as phenomenologically indistinguishable. So looking at two things and not being able to tell the difference between your experience of those two things. So to reiterate, our goal was to conduct an empirical test for whether brain states with different phi, so integrated information, can determine phenomenologically indistinguishable experiences. And we tried to do this by creating stimuli that appear identical, but have different neural bases in ways that matter for integrated information, which I'll go into a bit later. And the stimuli that we created we're calling filled, non-filled pairs. And these stimuli kind of make use of a phenomenon called perceptual filling in. And to give some background, perceptual filling in for vision is the insertion of visual properties. So for example, contour, luminance, motion into the visual field when those properties don't have any corresponding retinal input. This isn't a perfect definition, but this is our working definition. And the examples or the stimuli that we used are the petals illusion, which was developed by Kennedy in the 1980s. And it's black lines that are pointed tips towards the center. And at the center, you should see, I hope, that the center appears a brighter white than the background. And that's an illusory luminance. And on the right, there's an instance of the watercolor effect. So in the center, you should see a white identical to the background, but in the ring, in between the blue contours, you should see kind of like a light, faint blue ring, and that color is filled in. So now how to define filled, non-filled pairs. So we define filled, non-filled pairs as pairs of stimuli that appear identical. So they're phenomenologically indistinguishable, but they differ by physical properties and the amount of filling in that they generate. So at the bottom left would be an example of a filled, non-filled pair for the petals illusion. Maybe these look the same to you, but they're not, and I'll describe how they're not in this next slide. And on the bottom right, there is a watercolor effect filled, non-filled pair that might look the same, but they're not, and I'll describe how now. So to create filled, non-filled pairs, we start with the original illusion, which can be found in A, and then we extract or reconstruct the illusory properties perceived in that original illusion to create a reconstruction. So the reconstruction for petals and watercolor can be found in B. And then to create the non-filled member of the pair, we add the reconstruction back to the original illusion. And the hope here is that A, the original illusion, the filled member of the pair, will induce filling in the normal amount. And then by adding the reconstruction, maybe we're blocking filling in the non-filled member. So the rationale behind this is that the brain is making some prediction about what should be there based on the stimulus configuration. And if we provide that, maybe the brain need not fill in what's there. So we hope that A and C create images that appear phenomenologically identical, but differ by amount of filling in that they generate. So we conducted a pretty simple psychophysics experiment with this. We only collected data from 8 subjects, so it's pretty preliminary. But we basically tried in 3 different ways to create those reconstructions that I mentioned before. We had subjects themselves adjust stimuli in different ways to create a successful reconstruction of the illusory properties perceived in the original illusion. And then we used those 3 reconstructions to create filled, non-filled pairs and tested them to see if we could create them in the first place. And generally, the key finding here is that most subjects judged images in our pairs to be identical most of the time. So on the left has to do with the petals, not filled, non-filled pairs, and on the right has to do with the watercolor, filled, non-filled pairs. Each tile is one subject for one method of reconstruction, and the number there is the proportion of trials in which subjects judge the filled and non-filled images to be the same. So for most subjects and on most of the trials they did. Anything above a 0.5 means that they judged our pair to be comprised of identical or the same images. So now I'll go into why this is a challenge for integrated information theory. So this is mainly a challenge. This mainly could be a challenge for integrated information theory because the neural bases of filled-in versus sensory-based percepts differ. They differ in location. So sensory-based activation or sensory-based perception typically is associated with activity in lower visual areas, but filling in is linked to activity in higher visual areas, so V4, V5. In addition, within a cortical area, filling in is linked to activity in deep and superficial layers within a cortical column, but sensory-based activation occurs primarily in middle layers, and that's important for connectivity as well. So I'll bring that up again. In addition, there's a bit of a time lag. So filling in takes time. It makes sense. There's stimulus configuration, the brain responds, the brain fills in what it thinks should be there. So there is that lag when for a filled-in percept compared to a sensory-based one. And finally, and this is the most important for IIT, they appear distinct in connectivity based on the literature that we reviewed on perceptual filling in and its basis. So filling in has been attributed to more feedback connectivity than sensory-based perception. And there are two ways that filling in appears to recruit more feedback connectivity than sensory-based perception. First, it has been demonstrated that at least for surface color filling in, like in the watercolor effect, there is effective feedback from higher visual areas, so V4, V5 back to V1, so V1, V2. And this is where the layers become important again. The layer-specific activations for filling in also implicates feedback connectivity because in general, in the visual cortex, deep and superficial layers of cortical areas are targets of feedback projections from other areas, but middle layers are targets of feed-forward projections. So sensory-based percepts are activating those middle layers, they're going more feed-forward, and the filled-in percepts are activating deep and superficial layers, somehow recruiting feedback connectivity. And this matters for IIT because higher feedback connectivity generally means higher phi. So when we bring it back to our filled non-filled pairs, when we have on the leftmost side of the screen, the original illusion that's inducing a fair amount of filling in, right? We're getting stronger feedback connectivity. But if we can add the reconstruction to it and in C create the non-filled image that does not induce as much filling in, then there should be less feedback connectivity involved. So if we can get them to the point that they appear identical or they appear the same or judged to be the same by the subject, but they differ by amount of perceptual filling in and feedback connectivity, then we have phenomenologically identical experiences with distinct neural bases and in ways that matter for integrated information. So as a reminder, IIT predicts that brain states with different phi determine distinct experiences, but we were able to create a stimuli that in an ideal world, create two stimuli in an ideal world that appear phenomenologically identical, but have distinct neural bases by virtue of amount of filling in that they produce or yield. So this brings us to our whole entire argument. So filled-in experiences are determined by states with higher feedback connectivity compared to sensory-based experiences. So on the images on the left, they would be the original illusions. They would be the filled images, and they would be recruiting lots of feedback connectivity, lots of filling in. And on the right, with the reconstruction there, they're hopefully the non-filled images that induce less filling in and have less feedback connectivity. But we know that feedback connectivity increases phi. So the filled member of a non-filled pair induces an experience with higher phi, and IIT wrongly predicts that the experience of the filled member will be different from the experience of the non-filled member. Done.
Wow, Amber, you rocked the presentation. We have a little extra time, but we're going to move right on to the next speaker and hold the questions till the end of the session. Our next speaker is joining us from the Allen Institute, and it's Dr. Anton Archipov, who will describe the non-separability of physical systems as a foundation for consciousness.
Great, thank you very much. Thanks. Right. So yeah, I'll talk to you today about a hypothesis that non-separability, a property of physical system or of mathematical description of such systems, is a foundation of consciousness. So what are we pursuing here? Well, first of all, let's think about the definition of consciousness, which I'm using here to present this hypothesis. And the definition is the one that many people use, which is consciousness is the phenomenon of having a subjective experience. And so this definition, of course, is at the heart of the hard problem, which was articulated by David Chalmers in this conference, in the very first one, in the sense that we have physical objects, which we usually study in physics as objective observers. But some such objects, for example, brains, presumably, can have consciousness, the phenomenological first-hand experiences. So how does that come about? So ultimately, we want to understand how consciousness arises from physical constituents of the universe, such as fields, particles, and their interactions. And of course, there are theories that that proposed solutions to this. I'll mention just two here, which is the integrated information theory, and the other one is the orchestrated objective reduction theory, or OR2R. And both of them, or one of them, very well might be true and correct. We don't know yet, but I think it's fair to say that there are certain questions which are not completely covered by the theories. And so that's what I'm trying to investigate here. In particular, if we think about the IIT, the typical formulations of IIT operate with logical gates, things like logical gates, right? And their interactions. But what we are operating with in physics usually are things like particles, fields, Hamiltonians. And so the question is, how can we relate those to consciousness? And is there a connection maybe between a formulation of some theory that uses those concepts with what IIT proposes? And on the other hand, OR2R, of course, starts very, it's firmly grounded in just basic physics concepts. But even there, one can ask, well, is there any connection between OR2R and IIT, or are they completely orthogonal? Can we establish some such connections? So that's what I'm trying to address here. So the hypothesis is pretty simple. The amount of consciousness in a physical system corresponds to the extent to which the system is non-separable. What does that mean? So in physics, non-separability is a well-defined property. It simply means that certain degrees of freedom in a system cannot be described as independent variables, but need to be considered as a whole. And we'll talk a little bit more about how that can be written down with formulas. But why I find this an attractive concept to consider consciousness is because that directly, automatically establishes integration and boundaries. So when we think about consciousness, for example, in this paper listed here, Giulio Tononi and colleagues described very nicely some axioms that one might follow if one wants to define what consciousness is and what kind of properties a theory should address if it addresses consciousness. And I think perhaps the most important ones, at least I'll mention the two here now. The other ones I think are covered by the hypothesis that I'm proposing as well. But the two important ones are integration and boundaries. An experience, a conscious experience, is integrated as a single experience. The system that has this experience is also integrated. All the components that constitute that conscious complex are somehow tied together in a single complex. And it has boundaries. Some components of the system are in and some components are out. And that's exactly what non-separability gives you directly without any additional tricks. So mathematically, non-separability is usually formulated as shown here. Let's say we have a system with some degrees of freedom, x1, x2, and so on. We have a function that describes a state of the system, f of x1, x2, and so on. And usually that's a wave function in quantum mechanics, for example. So a system is separable if it can be represented, if this function describing the state of the system can be represented as a product of functions describing subsystems, such as shown here. A function corresponding to x1 can be separated from the rest. If we cannot represent the state of the function like that, then the system is non-separable. So let's look at a simple example. Here is a system consisting of 10 degrees of freedom. And in this example, we have 3 of those degrees of freedom, 1, 2, and 8, that are completely separable from everything else. I'm not telling you why they're separable and how, and there can be many details here, but let's assume they are. So in that case, the function describing the state of the system can be written down as a product of individual functions describing those degrees of freedom and everything else. And everything else is further decomposed into 2 systems, one consisting of 2 degrees of freedom, 9 and 10, and the remaining one consisting of 5 degrees of freedom, which are non-separable. And so what I'm saying here is that for a system like that, you can decompose it into 5 subsystems, 3 of which will be completely unconscious. They have 1 degree of freedom each. The other one that has 2 degrees of freedom will be a little bit conscious. There is some degree of non-separability there and just 2 degrees of freedom that are together, right? So like in IIT, I'm suggesting that consciousness is not a binary thing. It's either there or it's not, but rather it's a thing that can exist on a spectrum. And for this system, there will be some minimal amount of consciousness. And then for the bigger one with 5 degrees of freedom, there will be more consciousness. And in this hypothesis, the amount of consciousness depends not only on the number of degrees of freedom that are non-separable, but also how non-separable they are. I don't have time to go into details. There are ways to quantify it, but in principle, you can have a non-separable system where the interactions are so weak that for all effective purposes, it's essentially separable. And then, of course, the amount of consciousness has to be very low. All right, so that's the picture. There are 2 things that are very easy to show, which again, we don't have time for that now, but you can show that non-interacting systems are exactly separable and purely feed-forward systems are exactly separable and thus have 0 consciousness, which is by and large similar to what the IIT says. So just very quickly, discuss how this could apply to the real world. So the real world, of course, you can tell me, okay, this is a nice hypothesis, but if you look in the real world, there are all these objects that consist of interacting elements. And so they all are non-separable. Are they all conscious? Well, to some extent, yes. The point is that just again, like in IIT, anything that's even a little bit non-separable will have very tiny amount of consciousness. But there is this nice paper by Tegmark from several years ago, which describes very clearly how difficult it is to find truly non-separable systems in the universe. It's actually really, really difficult. Even for strongly interacting particles, you usually can find a rotation of degrees of freedom where you can, or transformation, where you see that that system is essentially all separable. And so what I think is happening is that anywhere you have a lot of small subsystems that have some non-separability, but brains are probably relatively unique in maintaining multidimensional states with high non-separability. And I don't think those states involve all the 10 to the 30 power number of degrees of freedom in the brain, taking into account all the elementary particles. Rather, it's some kind of macroscopic degrees of freedom, such as firing rates of neurons or maybe even firing rates of populations that exist in this non-separable state and create what we experience as a human consciousness. But it's probably a relatively small number of degrees of freedom, maybe thousands or maybe millions, but it's not 10 to the 30. That's my assumption. All right, one last thing I want to show here is a potential relationship between quantum and classical systems in the context of this hypothesis. So much has been said about potential involvement of quantum entanglement as a mechanism for consciousness. I don't have a strong opinion here. I think that's an interesting hypothesis, but of course there are challenges regarding how much of quantum states can be realized in the brain. I personally remain agnostic about that. But the interesting thing is that entanglement includes two notions: non-separability or non-factorizability of a state vector. That's what we were talking about so far. And non-locality. And that's a purely quantum mechanical thing, which is the knowledge of the state of one particle immediately tells us the state of the other, even if it's far away. And I guess what I'm suggesting is that if we take this hypothesis that I'm proposing about non-separability, it actually can work in classical systems. The system doesn't have to be quantum to be non-separable. It might be easier to have a highly dimensional system to be non-separable in a quantum case than a classical, but in principle, it's not a must. So, and then I think another point I want to mention is that there might be a useful formalism to consider this further, and that is actually the formalism using the Wigner function. So in quantum mechanics, typically one uses wave function, but the transition from a wave function to a classical analog is complicated at best. Wigner function, on the other hand, is this, it's an equivalent formulation of quantum mechanics. And it's connected to the wave function psi, as shown here with this formula. But Wigner function can be shown in a classical limit to become the Liouville density function. So there's a classical counterpart of the Wigner function, which describes the probability of the different states over the phase plane xp, right? This is a solid classical notion, and that function can be non-separable. So the point here is that you can have this seamless transition between the quantum case and classical case, and you can have non-separability in a classical case in principle. But the last insight that I want to mention here from that is that if we look at non-separability of the Liouville function, that is defined at the level of an ensemble, not a single trajectory, which we usually experience, right, or think that we experience, but at the level of statistical ensemble. And I think that's pretty profound. And also it has an interesting parallels with IIT, because in IIT, if you want to compute the amount of integrated information, you need to look at the state of the system now and all possible states before that could have brought your system to the present state, and all the possible states after that could happen after the present state and the probabilities of those transitions. So again, in IIT, it's not just the trajectory, the immediate one, which determines the amount of integrated information. It's actually a space of possibilities. And this line of thinking that I'm proposing here is having the same conclusion, or at least similar. So in summary, we are proposing here this hypothesis that non-separability of physical system is equivalent to consciousness, and it has this nice property that it's automatically establishing integration and boundaries. I'm suggesting that a convenient formalism to look at that can be the Wigner function and its classical counterparts, the Liouville density function. And if that's true, then consciousness is really a property of the ensemble and not a single realization of it. Or another way to look at it is maybe it's not so much the ensemble that is important, but rather the nature of the interactions, right? So you don't look at a single realization of the system, but you look at the whole Hamiltonian, for example. That could be another solution to this conundrum. Also, I want to mention here that the idea here is that when I say conscious, really what I mean is that the amount of consciousness is this property that we are talking about. The content of consciousness might be more of the immediate property of the trajectory, but the amount of consciousness is what I think non-separability corresponds to. So we talked about some parallels with IIT, the importance of ensembles, non-interacting and feedforward systems are non-conscious. And in terms of OR2R, I think there are some nice parallels as well, or at least they are not inconsistent, this hypothesis that I propose and OR2R, because, well, first of all, quantum entanglement is important in OR2R and non-separability is important for quantum entanglement. Second, I think if you have a wave function that collapses and gives you consciousness, you also can ask, well, how much consciousness does it give you? And the hypothesis that I propose tells you, well, that corresponds to the amount of non-separability in that wave function and how many degrees of freedom are involved. So finally, I hope that that may also help establish bridges between OR2R and IIT. So with that, I finish, and thank you very much.
Testing. Our next speaker is joining us from SUNY, and it's Craig DeLancey, who will talk today about IIT entails the complexity of consciousness hypothesis. Take it away, Craig.
Thank you. How am I doing? Do I have this up yet? I need to launch it. Oops. Sorry, I'm not a PC guy. How am I doing? That's yours. All right. I'm going to close it up. Okay. So while I'm looking here, if I can get rid of this. Maybe we should just put me there. Thank you. Thanks very much. So I'm going to defend this claim that IIT entails the complexity of consciousness hypothesis. And why does that matter? Well, there's this thing, I'm going to explain it to you tonight, the complexity of consciousness hypothesis. And it comes with a set of tools or implications or corollaries, which I think are useful. And I think it's interesting to see that, this one theory is able to assess and make use of this set of tools. So briefly, let me tell you about what the complexity of consciousness hypothesis is and the implications. It's sort of useful to start, I think, with a sort of thought experiment, which I think makes the underlying motivation really quite simple and clear. And I ask you to imagine, and I'll have to do this very briefly, given our time, but I ask you to imagine that, you're going to call a friend who paints, let's say, but has never seen a Jackson Pollock painting, and describe that painting to your friend over the telephone. And could you do that sufficiently well for your friend to be able to recreate the painting? Right? And you could, right? We understand that that is practically impossible. But why? It's in principle possible, but it's practically impossible. And why is that the case? Well, it's not because that's a non-physical object, right? It's because there's so much information in that picture, in that visual experience. It's practically noise, in fact. There's so much information in it, right? And so, and you understand as a speaker an expert speaker of a language, and as a human who's used to your memory capacity and so on, you understand there's sort of two limitations here. One is that bandwidth of talking to someone over the phone and trying to describe this thing. It's a very tiny, choked bandwidth, actually. And then you understand that you've got this capacity limitation also. Our short-term memory is not that big. Our medium-term memory isn't that great either. And there's a whole bunch of information there. And if I talked to you about it for 4 hours, you would have forgotten everything I said, right? So we have these two kinds of bandwidth limitations. You can guess what I'm going to say. I think this is analogous with many of the canonical arguments against physicalism. I think they're mistaking practical difficulties for ontological difference. So the complexity of consciousness hypothesis is the claim that a phenomenal experience of the kind that philosophers will pick out and say is mysterious is going to be, a proper description of it is going to be enormously complex. So I need to do two things here. I need to tell you, what do I mean by complex? And then I need to talk about that very, I said very descriptively complex. So the notion of complexity that I think is appropriate here is called descriptive complexity or Kolmogorov complexity. I don't know, is that something people are familiar with, or some of us are? Okay, I find it super intuitive if you just sort of think, if I just use a very simple example here. These are two strings. I made one of these up, and I kid you not, I made the other one by throwing 200 pennies in the air, letting them fall as they will, forcing them into a line, reading the ones as heads, the heads as ones and the tails as zeros. Now, which one of those did I make with the coin toss? It's just painfully obvious. It's the second one, right? And that is very peculiar because in classical statistics, they're equally likely to occur from the coin toss, right? They both have a 1 and 2 to the 200 chance of occurring. There isn't any sense in which in classical statistics you should say, oh, that second one is, you know, it's obviously the coin toss. But it obviously is, and it truly is, by the way, the coin toss. Why? You see there's a very simple pattern in the first string, and you know philosophers are lazy, and you think he's going to take the shortcut, right? And that second string, that's a lot of work, right? There's no pattern in it other than the whole string itself. And so that's what descriptive complexity or Kolmogorov complexity tries to grab. And there's some details about how we cash this out, but the basic idea is that the descriptive complexity of a description is the size of the shortest computer program that can print it or recognize it, and just that thing. Yeah, you have one type of computer and your friend has a different type of computer, but it is objective because different computers will get the same answer within some finite constant, which is independent of the thing we're measuring. Now, strings that we can't squeeze, we can call Chaitin random. That second string is probably Chaitin random, you know, given that if my coins were reasonable, right? We can't squeeze it anymore. I'd have to send you the whole thing if I wanted you to get that message. And it's an amazing fact that for any language, any sort of recursive system, you know, almost all people work in this area will just say all. You know, almost all of the descriptions are really close to Chaitin random. That's a sort of shocking fact about this, that, you know, this descriptive complexity reveals. So why does that matter? Well, you know, in the interest of time, I'll just talk about maybe this first principle. But if the proper description of phenomenal experiences is going to be very complex, then it puts certain constraints and pressures on how we understand and describe these things. The first one of these I call the modal judgment constraint principle. And it's just the fact that you can show that people's modal judgments is going to depend on how much information they have relative to how much information is the thing that we're trying to make a judgment about. And all the canonical arguments against physicalism are modal judgments. You know, you say, hey, you know, DeLancey, there could be this thing with the brain exactly like yours. It's possible that there could be this thing with a brain just like yours that doesn't have consciousness, right? Well, that's a modal judgment. And that's going to, you know, that's the reliability of that is proportional to how much information you have. These other two principles, I'll just say very quickly, they're principles that show that if you're trying to describe a very, or explain, excuse me, a very complex phenomenon, even if your theory can do it, it's going to take a lot of extra work. It's going to take extra information, even if it's a theorem of your theory, so that extra work and that extra information isn't premises, right? Descriptions of the world. Even in that case, it's still going to take a bunch of extra information if that thing is much more complicated than your theory. So what did I mean by vary? Well, I already said it. We have these narrow bandwidth that we use to describe consciousness. And so by vary, what I mean here is that the descriptions we use are going to be quite far below, right, the actual complexity of the phenomenon that we're describing. And then we have this channel problem also, this capacity problem, excuse me, where you know, our theoretical reasoning about these things is probably quite limited in comparison to the amount of information in the phenomenon we're trying to describe. That's not unusual, right? That's the way it is with weather. That's the way it is with certain parts of economics when you're trying to describe very big economic phenomena, right? You won't try and grab it in your head, right? You're gonna take your theory and you're gonna take a computer and you're gonna let it massage the data for you because it has a different capacity with respect to the size of that information. So what's the upshot of this? And of this complexity of consciousness hypothesis? Well, it has these corollaries, right? But the key one is that we can show that the canonical arguments against physicalism about consciousness would appear sound in these two conditions. Either it would appear sound if physicalism was really false, right? But they would also appear sound if the phenomena, you know, a proper description of this phenomenon of consciousness that we would need for the theory would have to be enormously complex. And in fact, that is true, right? The complexity of consciousness claim is true. And therefore, physicalism can be true, it follows. And I would say that given Occam's razor considerations, it seems like a pretty good bet. And we probably should put a lot of our eggs in that basket. You know, let's put some eggs elsewhere, but we should put a lot of our eggs in that basket. I gather from, you know, the theme of our topics tonight that people know about integrated information theory. It's an interesting theory. You know, this complexity of consciousness claim is a claim about a necessary condition on consciousness. It's not a theory of consciousness, right? But IIT aims to be a theory of consciousness to give us the sufficient conditions of consciousness, starting, you know, with this first person phenomenology, recognizing that our experiences are both integrated and differentiated. And the goal is to come up with this measure phi of the complexity of this integrated information. There, that word complexity is used in a different sense. And here's Tononi saying phi is the amount of causally effective information that can be integrated across the informational weakest link of a subset of elements. It would be nice if phi just entailed that the state involved had a high Kolmogorov complexity, but it doesn't, at least in the early forms of phi. And infamously, right, Scott Aronson showed that very simple kind of structure in terms of Kolmogorov complexity could have a very high phi value. And some people have interpreted that as a refutation of IIT. I think what it is it's a demonstration that we haven't quite got phi right yet. And maybe, you know, we just heard a talk perhaps in which we got much closer to the right measure, the right way to describe phi. Now you need that. I mean, if it's going to be a theory of the sufficient conditions of consciousness, they're going to have to get phi precisely correct. But what's the underlying inspiration, right? The underlying inspiration, the sort of target goal is this idea that consciousness you know, that we can properly understand consciousness as a state in a very high dimensional qualia space. That's the target idea. And looking at that, if you take another passage from Tononi, just making the same point, if you have a high dimensional space, this qualia space, and presumably in it, you know, blue is here, and I presume that, you know, different experience of blue may be slightly darker, it's going to be close to it in the qualia space, right? But tasting salt's going to be quite far away. But if this is a high dimension, you know, if we have this state and each of the dimensions can have at least two values, then most of the points in this space are in fact going to be very close to Chaitin random. That follows really simply. It's easy to show that. And then if it's a very high dimensional space, they're not only are most of the points going to be Chaitin random, but they're going to be describing them, locating, saying, here's, you know, describing that particular state is going to be very complex. So from this, we can say, I think, I'll skip that point. Given these reasonable assumptions, we can say that IIT is going to imply the complexity of consciousness hypothesis. And what's the benefit of that? Well, all these critical tools of CCH are available to the defender of IIT. You get a diffusion of the canonical arguments for anti-physicalism. You get an explanation of our stalemate of modal intuitions. You know, a lot of people look at IIT and they say, well, why the hell should that, you know, highly connected network be conscious? And we're going to explain why. Well, we're going to have different modal intuitions until we get into the very, you know, richly complex details. And it can explain why a productive theoretical approaches is a very similar point, isn't it? That the productive theoretical approaches can appear inadequate. It's, you know, the theories don't stand alone. You need this additional information to explain the complex phenomenon, even if the theory is adequate to it. But that's my main point. Thank you for your time.
Once again, we've had beautiful timing there. Next, we're going to hear from Matteo Grasso from University of Wisconsin, Madison. And he'll be telling us about the causal reductionism and why it should bug you.
Okay, thank you very much. Thanks everybody for being here. So I would like to talk to you about causal reductionism. And causal reductionism, as I targeted here in this talk, is defined as follows. It's the idea that only the unit level first order mechanisms really exist, really can cause, really can have effects, etc. The idea is very popular in neuroscience. We already heard about the astonishing hypothesis and the quote from Crick, who said that basically we are just a vast assembly of neurons. And the intuition behind it is really that first order mechanisms are sufficient to predict the dynamics of the system if we know the state of the inputs of each first order mechanism, a unit like a neuron. We can predict the evolution of the system, and therefore first order mechanisms are also sufficient to explain the causes and the effects that are at play in a system. For the philosophers in the room, this is clearly reminiscent of Jae-Gwon Kim's causal exclusion problem, which basically says that if we figure out what causes what at the most fundamental level, then we do not need to explain anything else. So if we know the causes of A and B, there is no need to ask what are the causes or the effects of A, B together. I will claim that causal reductionism is mistaken for two reasons. The first one is that it is inconsistent. It fails to apply the same criterion that it applies to first order mechanisms, which is a good one, to the irreducibility of high order mechanisms. And the second criticism is that it conflates causation with prediction. It assumes that since we can predict everything based on first order elements, we can also explain the causes at play. Most of 2/3 of what I'll say is the content of a paper that has been published last year in Nature Neuroscience with Larissa Bantakis, Jonathan Lang, and Giulio Tononi. I will add, so I cannot go into details, of course, but I invite you to check out the paper. I will add a little bit on this by just saying that this attempt was to characterize causation, but there is a clear connection to consciousness. So I will start by showing you a simple example. In this paper, we basically created a simple model with a simulated organism, a little frog living in a simulated environment. And the frog lives in this world where there are three types of entities: left bugs that are prey, right bugs that are also prey of the frog, and superbugs, which are predators. And the superbugs are the big, scary, three square large entities that you can see. So I will go through three examples of these little systems that have evolved to show you why I think causal reductionism is inadequate. So consider the first organism, and we call these F3 frogs. These have connectivity that is a neural network of logic gates. These are probabilistic gates. It has three sensors. It has three central units, which are basically the brain of the frog, and it has two motors. So the behavior of the frog is very simple. If it sees a left bug, it jumps left because SL and SC activate basically CL as a unit, and this in turn activates ML, making the frog jump left and catching the left bug. The same goes for the right bug, but the frog is also able to detect not only left bugs and right bugs, but also superbugs. And in this case, the central unit, CC, receives inputs, so represents the state of the world as there is a superbug, and is able to activate both motors, increasing the probability that they will fire, and it will jump over effectively, avoiding the superbug. So a traditional reductionist explanation of what's going on here is pretty straightforward. We have three mechanisms in the brain of the frog, and the central mechanism, CC, is the one that is responsible for the detection of a superbug and the function avoidance. And we can characterize, oh, this is, I'm sorry, this shouldn't be like this, but oh well. Okay, I hope you can see. Anyway, no, you can't actually. Sorry, is there any way to put this in light mode because you don't see the formulas? Let me try, maybe I can go back here. Sorry about that. Yes, it's much better. Okay, we can define exactly in a mathematical term what it means for the central unit to be causally relevant and to be irreducible. We can, for instance, apply causal structure analysis that we propose in this paper, or we can apply actual causation like developed by Larissa Albantakis and Giulio Tononi, or other measures of causal information. And we can basically show that if we were to partition the central node of this system CC, we would be changing the information that is specified about the state of the inputs by changing the probability distribution that the state of the node allows us to map onto the state of the inputs. And we can measure to what extent this node is actually specifying information about its causes, for instance, with this formula. In this case, we use alpha. This is a legitimate unit that has a cause. It is irreducible. If we cut it, then we lose information. And that's why causal reductionism is correct in claiming that this system can represent three states of the world: left bugs, right bugs, and superbugs, and the same on the effect side, but I will only comment on the cause side. But now the failure of causal reductionism is apparent when we consider another type of frogs. So let's consider F2 frogs that have evolved in the same environment, and now they just have two neurons in their brain because, of course, this is energy efficient. So interestingly, F2 frogs are functionally equivalent. They can detect left bugs and right bugs and superbugs, and they can jump left, jump right, and jump over. But they do so with having only two units in their brain. So now the mapping of representations and functions onto first order mechanisms, meaning single neurons, here is sort of problematic because we only have two units. And if we were to follow the dictum of Jae-Gwon Kim, in the moment in which the frog is detecting a superbug, well, the state of its left central unit has been caused by basically detecting a left bug, which is the left part of the superbug. The state of CR has already been caused by detecting a right bug. So there is nothing else left to be caused. There's nothing else that we need to predict that the frog will jump. The two units will activate together and the frog will jump. However, our criticism in the paper is that we can show that the same criterion for irreducibility and the measure of causation can be applied to second order mechanisms. In this case, we can, for instance, show that the information that is specified about the state of the inputs of the central unit L and R together is actually not reducible to the information that is specified about the state of their inputs of the two units separately. And we can do so exactly in the same way in which we have measured the informational contribution of a single unit that was CC in F3 frogs. Again, we can measure the contribution with a measure like alpha, but the question that I want to raise here is, what does this entail? Does it mean that we can always arbitrarily consider higher order mechanisms, like taking populations of neurons in the brain and finding that they exist on top of the parts, the constituent mechanisms that are single units? They specify more information? Do we have this explosion of mechanisms? Well, not really. And to see why, I think we have to go to a last example that is very interesting, I think. So consider the situation in which there are yet another type of frogs, which we call F1 frogs, which are effectively half frogs. They just have one node in their brain. And they are able to respond only to either left bugs or right bugs. So now, if it happens that these two frogs, by complete coincidence, find themselves next to each other in front of superbug, these two frogs will jump left and right, and they will again effectively avoid the superbug. So functionally, F3, F2, and F1 frogs are very similar. We could claim in functional and representational terms that their behavior justifies the interpretation that all of them, the three of them, have the capacity to represent three types of states of the world: left bugs, right bugs, and superbugs, and they are able to perform three functions: jump left, jump right, and jump over. However, it is possible to just show, in this case trivially to make it explicit, that F1 frogs are not a system and that CLCR is not a higher order mechanism, because a partition of these higher order mechanisms does not contribute information. Sorry, a partition does not does not cause a loss of information with respect to the information specified by the two units separately. So the first point is that causal reductionism is correct in identifying the causes and the effects of first order mechanisms, but it is inconsistent because the very same criteria can be applied to high order mechanisms. There is some causal information that is irreducible sometimes, not always, and therefore we believe that causal reductionism is limited in not recognizing so. The second criticism is that, and probably a reason why causal reductionism ends up believing that only first order mechanisms exist, is that there is a conflation of prediction and causation. So imagining this other simple case, we have this little system. It is trivially true and evident that we can, of course, predict the state of C based on the state of B prime if we were to record with two electrodes. But clearly, there is no causation going on. So prediction and causation can be dissociated. We know correlation is not causation. There is types of causal calculus, such as Judeas-Pearl interventionism and do operator, that allows us, for instance, to perturb B prime without perturbing B, and observing that now the probability distribution of node C is 50-50. So we can show that now there is no causation. But what I would like to stress here is that in all the cases that I mentioned, we can always predict what the system is going to do based purely on the state of the inputs. However, there is a very different picture of the causes that are at play in these three systems. So to sum up this part, causal reductionism basically would fail to recognize that F3 frogs, this system here, are actually very similar to F2 frogs, but they are both F1 frogs and F3 frogs and F2 frogs are very different from F1 frogs. Whereas like recognizing the role of high order mechanisms would tell us that F3 frogs and F2 frogs are both able to detect and effectively avoid superbugs, whereas like F1 frogs are not. So causal reductionism basically is ignoring the similarity between the first two systems. Finally, I will conclude by just saying that, well, clearly this analysis has been informed by some calculations of integrated information. In this case, it is a simplified version that we call actual causation that ignores the properties that are specific for integration of a system. But it is important to stress that high order causation is also crucial for consciousness. And the reason is that when we consider some mechanisms in the brain, we may be tempted to just use 4 units and say, these 4 units are all we have. But if we do apply the mathematics of high order causation, we would actually have to consider all the high order mechanisms that are possible. Not all of these would exist, but we have to check because the information that they can contribute is can be as irreducible as the one of first order mechanisms. And of course, each of these mechanisms could have different causes and effects, and this contributes to the complexity of the experience. In the brain is not only 4 units, is a lot of units, and this could be relevant to explain the richness of experience that is a problem in neuroscience. So to conclude, causal reductionism is mistaken because it is incoherent and because it conflates causation with prediction. In the paper, we just show this part of causation, but a connection with IIT shows that recognizing the role of high order mechanisms is necessary in order to explain complex contents of experience that are contributed by populations of neurons. For instance, one neuron in my visual cortex and one in my auditory cortex may form a high order mechanism. And ultimately, this may explain the unification of all these mechanisms into one single conscious entity. However, this is the part that IIT deals with, and the calculation is a little different. So please check the paper if you're interested in more. And if you have any questions, please ask. I'm always available during these days, or you can email me. Thank you so much.
Well, thank you. A little buggy, but still very interesting. Next, we're going to hear from Angus Nisbet, who's coming to us from Sussex and the National Health Service. And he'll be telling us about the machine is a ghost, a new argument from physics for metaphysical idealism.
No, it's not. Okay, thanks very much. So I'm a neurologist from Sussex, and I'm writing a book on consciousness, and I'm talking on 2 subjects that I don't have any natural or official expertise in, which is philosophy and physics. What I want to do is, using Gilbert Ryle's phrase, the ghost in the machine, turn it on its head. And what I want to do is to undermine your concept of the physical a little bit, to make it a bit more shaky, first of all, from a philosophical point of view. And then, having done that and left you a bit shaky about what you conceive and conceptualize as the physical, I then want to turn to physics, and I want to then undermine it from the other end. So here goes. So famously, René Descartes described in a couple of his works the body basically as a machine. And he also famously divided his ontology divided the world, or the universe, if you like, into, or what there is, into the physical realm and the mental realm, the res extens and the res cogitans. And the idea was that the physical realm had extension, size, and location in space, whereas the mental realm didn't. This, of course, left him with the so-called interaction problem, which, of course, the famously Princess Elizabeth of Bohemia picked him up on. We haven't got time to discuss that. So whiz forward to the 20th century, and a philosopher called Gilbert Ryle, who interestingly was born and bred in Brighton and educated in Sussex at Brighton School, became a professor of philosophy at Oxford. And I don't know whether you know this, but I think he was Dan Dennett's PhD supervisor, which is quite interesting. And that's him in his various iterations. He started off very serious and looked a lot more relaxed at the end. I thought they were quite interesting pictures. Have I talked? Yeah, so he wrote this book called The Concept of Mind in 1949. Most of what he says in the book is really based on his argument in the first chapter, that the idea of Descartes, that there was a spirit, as it were, or a mind trapped, or not trapped, but inside a body, but different from a body, which had been the official doctrine in the sense that it was the scholastic doctrine of the church as well, you know, from Augustine onwards, and probably even St. Paul, although his ontology is a bit difficult to decipher. But basically, he called it the official doctrine, and he admitted that he was going to be abusive about it, and he called it the dogma of the ghost in the machine, or the myth of the ghost in the machine. He said it was a big mistake, namely one big category mistake. And he made his argument based on 4 analogies, and I haven't got time to go through all 8 of them, but I'll just pick the most common, the most well-known, which is the visitor to Oxford or Cambridge University that comes along and says, well, I've seen all the buildings, and I've seen you know, the playing fields, and I've seen this, that, and the other. But where is the university? But of course, what Ryle had actually done inadvertently was actually make a case for 2 separate categories. And I don't know how he got away with this, but basically, I think he, you know, if you translate that to the mind and the brain, he was effectively saying, I've seen the body and I've seen the brain, but where is the person, or where is the mind, if you like? So I think actually it was Ryle who made the category mistake. He made the mistake of category denial, which I would argue is also what illusionists and some eliminative physicalists make the same mistake these days. Now, actually, Aristotle, if you've ever read De Anima, it's a wonderful read. But he made the same point, and this is the only bit I'm going to read out because I think it's just worth reading. He said, it is the same in the case with a house. The rationale of a house will be something like this: a covering preventative of destruction by wind, rain, and sun. But while one philosopher will say that the house is composed of stones and bricks and beams, another will say that it is the form of these things that for the given purposes, the ones he's just said about shelter against a storm. Who then is the natural philosopher among these? Is it he who defines it in terms of its matter and knows nothing of its rationale, or the one who defines it only in terms of its rationale? Or is it rather the one who defines it on the basis of both, which of course is what he's going for? So clearly Ryle failed the natural philosopher test set by Aristotle. Aristotle, interestingly, I don't know whether anyone knows this, was the first person to describe the hard problem. That's another quote from De Anima. in which he says that it's one of the hardest things to gain any conviction about the soul. And of course, David Chalmers, as famous for the modern formulation of this problem, which of course has gone back through history, and it was called the explanatory gap by Levine 30 or 40 years back. Interestingly, reading David Chalmers's paper, his 1995 paper, which I gather was tied to a presentation here at Tucson, he actually jumps in his formulation. His first formulation is what I call a correlative definition of the hard problem of consciousness, where he's basically saying, why is there anything happening why do we have experience at the same time? He uses the term when, and then later on he slips to using what I would call an emergent definition, which presupposes that the physical is primary and that somehow the consciousness is an emergent, emerges from the physical, which is interesting. So I think that was an interesting slip. I'm not going to say much about Dan Dennett because it's difficult to quite pin Dan Dennett down. And I think he would deny that he's an illusionist about the mind, although there are definitely some illusionists. There's one in England called Keith Frankish in Sheffield. I did think it was interesting that Dan Dennett looks, just as Aristotle looks a little bit like, or David Chalmers is beginning to look a little like Aristotle. I think Dan Dennett looks quite like Democritus, but that's just a point of note. So what are the issues with physicalism? In other words, denying the sort of separate existence of this other realm, the realm of the mind? Well, the first thing I would say is what I call the Cartesian Augustinian trap. The first cogito, in fact, was by Augustine 1200 years before René Descartes, but I haven't got time to go into that. But if you say that the I, the person, the conscious receiver, perceiver inside is an illusion, then then you have to, an illusion has to be experienced. You have to be illuded. There has to be an I. So I think that there is a problem with that. I think there's also the problem of category denial. We all know that we have a mind and that there is a mind and consciousness. And I think it's also self-refuting in the sense that if someone ascribes to that point of view, then who are they? They aren't a person if they don't have a mind. You could argue that. Anyway, now, the rot set in with René Descartes because one of the other things he said was that actually our perceptions of the physical were very unreliable. Well, they were not very unreliable, but they were certainly more unreliable than the contents of our mind. We knew the contents of our mind more closely than we could know the physical, and we could be deceived about the physical, but we couldn't be deceived about the fact that we were having an experience. So that was what he said. Bishop George Berkeley then famously came along and brought along the modern era version of idealism, the idea that everything is thoughts or ideas, as they used to be called. And he based this on the fact that if you internally introspect about your perception, you realize that all you perceive is qualities, and that's all there is. And if there's only qualities, then maybe that's, he sort of jumped to the conclusion from that there was nothing else apart from qualities, and qualities were properties of mind. They were just ideas in the mind. And so he famously said, everything is mind, or everything is ideas, which upset Samuel Johnson a lot, who famously kicked a rock and said, "I refute you thus, Mr. Berkeley." But in fact, if Samuel Johnson was to know a little bit about modern physics, I don't think he'd have kicked the rock quite so hard. And that's what I'm hoping to convince you by the end. How are we doing? Yeah, we're doing okay. So Hume put Berkeley right, because he said, you can't really jump to the conclusion of idealism. All you can say is you can't really be certain about the external world and its nature, and even that it's there. And then Kant came along, and basically, I haven't got time to go through Kant because he's very complicated, but basically a key message of Kant is that we can't know what is actually out there, because it is filtered through our perceptions, which come through our sense organs. The other problem with our conception of the physical is language barriers. If you know anything about language, and I don't know very much, but it's all based on metaphors. And if you think about chairs, we talk about their legs, their back, their feet, the face of a clock. And this applies, of course, to our concept of physics as well. We think of, we try to explain things or metaphorize things to what we experience at our bodily Newtonian level, our everyday level. So we talk about particles, thinking about ball bearings. But of course, if you could get down to the size of a particle, which we can't, you couldn't roll it between your fingers. It wouldn't have any solidity. Solidity is an emergent property. We talk about waves based on our observation of the waves. They're all metaphors. Even fields are metaphors. They're three-dimensional versions of swaying wheat fields and so on and so forth. And the other thing to say is that the only way we can express our knowledge of what is, the underlying ontology of what exists, is either in language or in mathematics. And if we express it in language, we've got this problem, of metaphors. We've also got the problem of definitions being vague around the edges, which I haven't got time to go into. And if we express it in terms of mathematics, then it's difficult to get our heads around it and understand what it means. So we seem to have to use both. Just a very quick thing about space before I move on. Space, basically, Aristotle pointed out, shape and size is determined by feel initially, and then we translate that into sight in the sense of moving your fingers along, how far you have to move your fingers, or indeed your eyes, along an object. And that gives you the idea of shape and size. Russell Brain, British neurologist, talked about the same thing in relation to space, and that we determine a distance by how long we've been putting in the effort of, for example, moving our arm from one place to another, or from walking to one place to another. And then greater distances we work out by comparison. So that's again maybe that's all space is. It's this kind of action-time complex. So in that sense, that's supporting what Berkeley said, that primary qualities are just the same as secondary qualities. They're all body dependent. We come to the crux, which is Hempel's dilemma. Hempel basically said it's very difficult to define the physical, because if you define it with reference to contemporary physics, for example, the standard model, which I've got there, it's incomplete because physics is incomplete. If you alternatively try and define it via reference to an ideal complete physics in the future, then you've got a problem, because you don't know what that is. So that definition is very, very woolly, and he called it trivial. So so I think that's all I need to say about that. So I've just proposed here a definition of the physical, which I think probably I'd be interested whether you agree with, but this is what I propose, that the realm of all entities, this is the definition of the physical, that have been or have the potential to be or could ever have been. So this is kind of the idea that we've got to sort of do it before we arrived on the planet. But it's got to be reliably intersubjectively experienced by human beings via the sense organs, either directly or assisted by scientific instruments such as the LIGO interferometer, which I've got on there, or Geiger counters or mass spectrometers. So I'm saying that I don't think you can define the physical using these models. You have to define the physical in terms of the human body. And I think that's really what we do when we use these metaphors. I'm going to miss out that. Okay, so here's the physics. I'm going to whiz through it. I'm not going into great detail because you know about all the physics, but I'm going to take you down the rabbit hole now and undermine your concept of the physical, hopefully, from the point of view of physics. Are you ready to take the red pill? Here we go. So what's holding these two Chinese boys up? And the answer is glass. They're on a glass bridge. Which just is an illustration of how empty matter is. In fact, solid matter is 99.9999999% empty. And that's provided you assume that the protons and the neutrons and the electrons are solid, which of course they aren't. So matter is actually 100% empty. Everyday physics, we don't have to go to quantum physics to start to get worried about our concept of the physical. We've talked about the transparency of glass. What about gravity? Newton was very troubled by gravity because it had instantaneous action over a distance. Okay, Einstein explained it by the bending of space by mass, but it's still a bit of a problem. Gravitational waves still are limited to the speed of light, but gravitation itself is instantaneous over distance. Then there's magnets. You know, when we're children, we're fascinated by magnets, but we've got so used to them that we don't really have that fascination anymore. But it's strange that they're acting over a distance. Yeah, this is all to do with fields in physics. But what are fields when you start to think about it? Why do electric motors work, which use these principles, the electromagnetic Faraday's laws and so on? How does light travel through a vacuum? And then, you know, I don't need to regale you with quantum mechanics, indeterminism of radioactive decay, for example, the fact that solidity just arises from Pauli exclusion principle, from a system of rules, wave-particle duality, and so on and so forth, cosmology. So the physics, I would argue, is
let's wrap it up. Jump to your last slide, please.
Okay, I'll whiz to the last slide. So physics, I argue, is fundamentally phenomenal. So the physical is fundamentally the phenomenological. If you were to take a journey into the human body and go down various information levels, when you got to the bottom, you might just find mathematics waiting for you at the bottom and nothing else. Matter seems to be empty, space seems to be full. So maybe and I haven't got time to go through the argument, but maybe if you think about it, fundamentally, matter is like everything fundamentally is the flow of information according to rules and mathematics. So it's a bit more like a mind than anything else. So if it's a bit more like a mind, or a bit more like thoughts, then maybe there's a big, giant mind, as it were, to contain it all. And you might like the idea of the cosmic cogito, which is the universe thinks, therefore it is. But the point is, the physical machine of the body appears to be fundamentally comprised of dynamic, interacting contents of a mind or a geist or a ghost. So I conclude that the machine itself is a ghost. Thank you very much.
Next, we'll hear from Uzi Awret, who's joining us from the Inspire Institute to talk about the strange metal theory of consciousness. Is that right, or did we lose the N? The metal, is that mental or okay.
Sure. Yeah. Okay. Hi, so my name is Awret, and I'm going to talk about two papers that one of them just got published. It's called Holographic Duality in the Physics of Consciousness. If anyone's interested, I can send it to you, because I don't think that I will have a chance to cover everything. And since I'm using or I'm relying on physics that can be considered a little strange, then most of this talk is going to be actually dedicated to a more general approach, or perhaps a theoretical framework where you can somehow have strange physics and theories, philosophical theories of mind interact fruitfully. So the first thing that I'm going to do is take the approach of a problem solver towards the hard problem. Okay, so let's say that we want to approach the hard problem. A problem solver would first see, okay, it's a very hard problem. Let me look for a slightly easier problem that still constrains it. And you can keep on going like that, perhaps generating other problems that are successively easier, but that still constrain the problems that generated them. And in the end, you can reach a problem that is perhaps easy enough and hard enough to matter philosophically. So this is what I'm going to do. And so I call it, you can think of it as a certain path of least resistance. And this is especially true for consciousness realists. So because eliminativists can be treated differently here. And the first thing that I'm going to do is replace the, or move from the hard problem to the meta problem. Those of you who had a chance to read David Chalmers' 2018, The Meta Problem of Consciousness, then it provides a certain strategy and at least claims, and perhaps for good reasons, that the so-called meta problem constrains the hard problem. And if you want to think about the meta problem, there are a lot of ways. It's really the problem of the problem, or why is the problem of consciousness? Why does it seem categorically different than other problems? Why is it so hard? And a useful way of thinking about it is thinking about trying to show that smart enough artificial intelligence would eventually generate similar statements to the ones that we do about our own internal states. And this, of course, comes from the zombie argument. And in the zombie argument, it's enough, a behavioral zombie, it is enough to find, let's say, one statement that zombies are not likely to make to show that they're inconceivable. However, and to find such, if we're looking for such statements that zombies may have difficulties with, then they're probably statements about our own consciousness. So statements, for example, conscience reports. I am conscious. I'm sure that I'm conscious right now. So this is an example of a conscience report. You can also have problem reports, so-called, and these are reports like, I can't believe that consciousness is physical. Okay? So the idea is that, can you show that a smart enough AI who is not conscious will still be able to generate similar statements? And obviously this is related to the Turing test. So for proponents of the conceivability argument, it is crucial that you can actually solve the meta problem and show that it is likely for a smart enough AI to generate such statements. And actually Chalmers did that, or was going in this direction at the age of 18, where he wrote one of his first papers on smart beings. And those were exactly, so first you want to show that it makes a lot of sense that they will develop self-representation, and you can slowly build perhaps a sense of the physical, and slowly you can show that such beings are likely to generate statements that are similar to the ones that we generate. So, and of course, the meta problem is also crucial. A solution to the meta problem is also crucial for eliminativists, right? If you're an eliminativist and you don't believe that, you think that consciousness is an illusion, then you still need to explain exactly the same problem. So it's a very interesting problem, and I'm not going to get to because there are arguments whether it does constrain the hard problem or not, but let's say that it does. And it is definitely the hardest easy problem, okay? And so I'm saying, so it does make sense then to move first from the hard problem to the meta problem. However, the meta problem, as we see, it contains a lot of different sub-problems. So there's a lot of sentences or statements that would be difficult, perhaps, for a computer, a non-conscious computer, to generate. Some like the ones we discussed, but Charles himself talks about negative and positive so-called problem intuitions. So you'd like the computer, for example, to be able to say things like, I think that any conscious system should somehow have a feeling of what it is like to be. Okay, so a computer this would be a positive problem intuition. You'd have to explain why a computer would say that. And then you can have anti-physicalist intuitions of the kind, I don't believe that consciousness is physical, or I don't think it's possible. And so what we're going to do now, I'm going to make another simplification and only concentrate on anti-physicalist problem intuitions. And here we are actually we're kind of embracing Daniel Stoljar's ignorance hypothesis. I don't know if those of you are familiar with it, but it simply says the ignorance hypothesis says that we are ignorant of physical facts such that had we known them, it would have explained away our anti-physicalist intuitions. Now, Stoljar has different versions of the ignorance hypothesis. Here I'm going to adopt the most conservative one, meaning that I will claim that you can use standard physical facts that can actually explain away our anti-physicalist intuitions. Or this is then a conservative version of the ignorance hypothesis. And so as soon as we restrict ourselves to anti-physicalist intuitions and standard ones, then we're making a very conservative move. And from that on, you can include the next step. And oh, by the way, you can also think of the meta problem of the soul strategy, and this is actually common to both Stoljar and Chalmers, as really having a different way of looking at the hard problem. And the idea is that metaphysical theories of consciousness, that is, how does matter gives rise to consciousness, should have some kind of an essential chapter on how consciousness acts back on the brain in order to generate statements like, I am conscious. And this is a very hard problem. Some say that just as hard as the original hard problem. And we can think of these two problems as two sides of the same coin, in a sense. But they definitely seem to be related. And Stoljar himself says then that it is important to understand how and whether and how consciousness can act as a cause for everything that we know and say about it. Obviously, if I can solve the meta problem and show that everything that we say about consciousness, for example, can be generated without consciousness, then we may have a problem, because if we believe that, then it becomes harder to explain how whether consciousness really causes what we know about it, and that obviously is a problem. So in a way, you should treat theories of consciousness in such a way that you should really conjoin both problems and try to satisfy both together. And obviously this creates a problem for consciousness realists, right? Because if you are conscious realist, you believe that consciousness is real, then you have to take a stand on the meta problem. So you have to say, okay, either I think the meta problem has a solution, and then you have so-called the meta challenge, where you have to explain really how consciousness can give rise to everything we know about it. And obviously, this is a problem. So we can call this the more symmetric approach. And we said, therefore, so some of the advantages of using the meta problem first is first that it is symmetrical. It constrains the hard problem. But one of the most interesting properties, in my opinion, is that because there are so many different problem intuitions that need to be explained, we can perhaps start with the easier ones, maybe choose 2 or 3 easier problem intuitions and explain them, and then maybe use these explanations to help explain some of the harder problem intuitions. So, this is an approach that, in a sense, says, okay, let's suspend the strategic suspension of the hard problem. Let's not ask momentarily questions about the hard problem, and first try and solve some of these easier meta problems, and then maybe we'll be in a better position to lift the suspension and see if we can say anything or somehow use these solutions to solve the harder problems. It's also important to know that the meta problem can have a lot of, it can have, we said, a lot of different solutions. And so you need somehow to choose some easier meta problems that can be important to understand issues that have to do with the hard problem. Another step that we can do to simplify things is to separate so-called representational content and phenomenal character. So the conscious mental state has, in a sense, both so-called phenomenal character, which is perhaps not structural and maybe harder to explain and common to all conscious states and systems, but it also has structural properties. And the structural properties of the phenomenal state and the structural properties of the physical substrate that generates these phenomenal states, right now they seem to be almost independent, meaning at least we have the intuition that the two are do not depend on each other, and so I call this the structural mismatch problem, and this is one problem intuition that we can try to explain, because again we're trying to relate 2 structural domains, and our chances are better. So it's definitely something that I would like to do before I can actually try and tackle issues that have to do with phenomenal character, for example. So this is another way of making another step towards an easier problem. And one of the advantages of combining this with Daniel Stoljar's ignorance hypothesis and so-called epistemic view is that if I can find a single physical explanation that can explain 2 different problem intuitions, the easiest ones that I can find, then because of parsimony, a parsimony argument, I can say that there's a very good chance, or a reasonably good chance, that this physics may have some kind of bearing or it will prove important to some of the harder problem intuitions. But this is true if you actually find a physical explanation of your anti-physicalist intuitions. And this is not easy to do because physics, for example, has to be rich enough to explain away the conceivability of zombies, or at least explain why the conceivability of zombies does not threaten physicalism, for example. And this is not an easy thing to do. The physics would have to be pretty strange or have some special properties. Okay, so this is an advantage of adopting Stoljar's ignorance hypothesis. Right, so until now, I've really tried to combine the meta problem by Chalmers, the ignorance hypothesis by Stoljar, and the third thing that I'm going to do, because we do want to make things easier, is commit myself to physical facts that have something to do with the neural or physical correlates of consciousness, okay? Meaning that I think makes perfect sense, right? So the physical facts that I'm looking for will have to do something with the neural correlates of consciousness. However, here we run into problems. For example, there's the Krigel's empirical equivalence problem, where he seems to suggest that it's not likely that we're going to make any empirical findings about the physical correlates of consciousness that will enable us to choose one theory and not another.
Wrap it up.
Okay, so obviously I don't have time to go over. Let me just add that in order to make this whole approach more powerful, I'm also committing to the so-called Ross and Ladyman's principle of natural closure, which in a sense insists that one of these, or if I find some empirical facts, let's say about the NCC, it would have to have at least one premise that has to do with fundamental physics. If you combine all these, I argue that you get something that has to do with the holographic duality and this very kind of fancy physics. And again, I'd be glad to send the paper to anyone. So I'll just finish here as some kind of a theoretical framework that can take you somewhere.
Thank you.
Okay, thank you.
Certainly falls into the realm of heavy metal. Our last speaker is Gerard Blommestijn from Amsterdam, who's going to talk about how the space-time metric tensor fields in microtubules can encode the qualia of conscious experience and choice.
Well, thank you all for coming to my talk on this late hour. I will start with the Godel Theorem that Professor Penrose uses to show that quantum mechanics is needed to explain mathematical understanding. So here we have how Godel, or how it is considered, and we'll go fast over this. But what is also necessary to know that is that you can say a Godel statement, that the Godel reasoning is that you have statements that are not possible for the system to know whether they are true or not, while the human, the mathematician can understand it. But then you can say, okay, but you can make a new system, algorithmic system that is better than that and that knows of these statements what then the value of the truth is of it. But then you can have in that new system, which is bigger, again, these Gödel statements. So you come in what is in red there, an infinite regress. And but the main thing of this is that Penrose showed that therefore you need something in the understanding, mathematical understanding, that is better than algorithmic, better than computational, in the sense that so that classical physics, which is computational, which is algorithmic, is not sufficient. So that means that quantum mechanics is necessary. And then where could we find it? And the idea was, anyway, in the shadows of the mind, that you find that in microtubules. So then you have microtubules in cells which are coupled by microtubule adjacent proteins. And so a microtubule consists of tubulin proteins. And these tubulin proteins, they have structure with amino acids, of course. And these amino acids, the so-called aromatic amino acids that have these hexagonal carbon rings in them, of which the idea is, has come gradually in the hammer of Penrose paradigm, that the p-ring interaction, so that, so to speak, the electron cloud of one of such a group of 6 carbon atoms may interact with another one, and they're close enough, they're on the 1 or 2 nanometers distance. And so the idea is they can form kind of networks that by means of these interactions of the it is in fact chemistry, with quantum mechanical chemistry, and they are in fact using the London van der Waals forces to push each other, so to speak. These and so you get very big networks, or anyway, you have the possibility to get very big networks of synchronized coupled activity along all these p rings in the amino acids, and then over the different tubulin molecules in the microtubule, and then perhaps with gap junctions to other cells. So here you have then kind of an image of the bigger structure that you could get. And so you get large resonating networks of pi rings. And then in the Penrose-Hameroff paradigm, there is this objective or orchestrated objective reduction. That means you have a moment, it is a purely physical process, but you have a moment of what they call proto-conscious experience. So that it is some kind of experience, and with proto-conscious, it means that already on the small level of very simple reduction, you have a certain amount of observation, a proto-conscious experience. But then the question is, what is then this I that perceives? Because it is, if it is perceived, if you perceive something, it is always an I, a consciousness that perceives. Now, von Neumann has written about this in his book about the foundations of quantum mechanics. And this is an image of John Bell, who puts the cut between the quantum system and the observer on different places. You have there the different possibilities, but at the last moment, most deep into the brain, he even says it in the way that it is behind the brain, just in front of the abstract ego. So not exactly how John Bell draws it, but it is more with this red line. And he calls that which experience the observation, the abstract ego. Here I have the passage from the book of John von Neumann, where he introduces this abstract ego. It is, you have to go through it to understand it in mountain gear. Not you cannot do it quickly, but I just made a copy of it. And one important thing in it is that you have two kinds of processes in quantum mechanics. One is the discontinuous, so that is the observation, in fact, process one. And process two is the automatic unobserved waving on, so to speak. And now I come to the third part of the talk, that is that is about all the types of experience that this abstract ego has, what modalities there are, and how that can be in the neural correlates of consciousness, or the microtubular correlates of consciousness. So I'd like it to start with the Platonic ideas, because they give some kind of structure in our experiences. I have there these two processes. You have the Platonic value of a Platonic idea that goes on adventure in the real world. For instance, the circle, or let's say the flat plane is on adventure here as the floor of this room, for instance. But so there are myriads of things that of these Platonic ideas. And in the other way, when you recognize a Platonic idea, you could call that abstraction. Now, the abstract ego perceives the totality of all these perceptions. So you have the rational perceptions, that's where it started, the mathematical understanding of, for instance, of the Godel statement. You have all kinds of understandings. So that is the rational experiences. Then you have sensory perceptions that are the senses, those experiences, and emotional perceptions. And the qualia and all those perceptions are manifestations of ideas, of forms. So ideas of forms are simply the Platonic ideas that you can abstract. For instance, when a child learns the natural numbers, you place of a certain one of something and two of something, and at a certain moment the child understands what the numbers are, and at that moment you could say he has contact with the Platonic world, with the Platonic concept of natural numbers. Then on the physical side of the orchestrated subjective reduction, a certain geometry is selected. If you have, for instance, these two possibilities that you see on top here, and they are in superposition. They're in superposition, and then one of these space-times is chosen. That is the objective reduction, and that is in fact a curved space-time geometry which is selected. If you look at it as you can look at it like quantum mechanical wave functions when you look at the electromagnetic aspect of it. So the electromagnetic wave functions of these pi rings. But these pi rings are movements. They are in movement of the nuclei and the electrons. So they are in fact some kind of geometry, space-time geometries, because space is curved a bit around masses. And it is as if John Archibald Wheeler has said that so beautifully, space-time tells matter how to move, because matter moves along along the curvature of space-time, and matter tells space-time how to curve. So the places of the particles, they determine the geometry at a certain moment. For instance, the geometry of a resonating enormous amount of pi rings in microtubules. So this is in fact the outcome of an orchestrated objective reduction, and that you could call then the neural or tubular tubulin correlative consciousness, and that this structure represents exactly what the living being understands and sees, etc. Okay, this is not the whole story. It is not one-way traffic between the neurons and the abstract ego. Also from the abstract ego to the neurons, you have traffic, namely the choices that that consciousness within an organism makes. So altogether, this is a grand generalization of the Platonic ideas. Then I consider these Platonic ideas that in the curvature of space-time, on these pi rings, for instance, in the tubulin, in the microtubules, you have a way of describing that by means of the metric tensor. That is the way in which the relativity theory describes the curvature of space-time. And so my idea is then that these Platonic ideas are kind of letters, words. They are the primitives from which the whole experiential and also the choice perspective is built from. It's of course enormously complicated, as we know of our experiences. And let me see, this was the last already. Yeah. So yeah, I hope I have been able to bring over to you this idea that the curvature of a certain chosen geometry in an objective reduction, orchestrated objective reduction, that it is built up of all kinds of space-time forms, space-time curvatures, of which every space-time curvature is a kind of perception and a kind of choice. So you have for every type, you have a certain form. That, okay. Thank you very much.
Thank you, Gerald. Gerald, would you be so kind as to grab that portable microphone? And if you can come down here and join the other speakers in the front of the stage, we'll open up the discussion, including questions from the audience and for each other. So our at-home audience can see us. Anyone with a question should come up to the standing microphone, and in fact, you can line up down that aisle. Since there's no lineup, I get to ask the first. Okay. Yes, sir.
Okay, I have a question for, it's more of a comment for Amber. So full disclosure, I worked in Tononi's lab for 4 years, and I am committed to IIT. So my comment is, I think your paper is amazing. It's exactly what IIT needs, because there's a lot of papers that misconstrue parts of the theory, and they don't really deal with the exact formalism or exact notions, but your paper and Kelvin's paper is really good under this respect. So there are two things that I want to bring up, and you discuss these two aspects in your possible replies section, which is, again, a great virtue of the paper. So the first one is, based on the literature that you have reviewed, do you have any ideas of, I know this is a hard question, of the extent to which phi may change? And I know we don't even know this question because it's very hard to compute phi in a real brain for now. But I think at least your paper is a proof of concept. Like, this type of experiment is what could really test IIT if we had a proxy for phi. And what do you think of the claim that, well, the difference in phi might be, again, there might be a threshold above which a difference in phi is noticeable. Would you think this is a problem for the theory? There's many conditions. Of course, there's change blindness, where phi definitely changes. Report seems to report no change. There is even anosognosia, where people are dramatically, I mean, clearly they have a different experience, but they don't notice. So I was wondering if you think that this is a big problem for the theory, and this connects to the report, of course, question. Right, thank you.
Yeah, thank you. So yeah, that has to do with whether or not it's accessible or noticeable from the point of view of the subject. So maybe there is a difference in phi, but if it's not noticeable from the perspective of the person, maybe it doesn't matter, right? Like, maybe the conscious experience that you have is too macro to notice small differences like that. Where I think this might be relevant for the question and the comments that you had. Whether or not the difference matters, I think, has to do with what's excluded. So whatever is contributing to phi max, right? So if it happens to be that the differences between phi in the, when viewing the two images in the pair, while they're distinct in space and time, right, in that qualia space sense, maybe they are excluded in what's actually contributing to the conscious experience. So maybe they're in that way too low level. I don't know if that's relevant, but I felt like maybe that was helpful.
Sure. And have you thought about using PCI, since you do TMS and BG?
Yeah, I suppose. I don't know if I would predict a difference in PCI with the two. I mean, that seems more helpful in a level of consciousness type situation. But yeah, the next steps, of course, for these pairs would be to study the neurophysiology and see what's actually happening in terms of connectivity. And then that has the most bearing on IIT. Thank you.
So my question was about this interesting idea of this more general notion of non-separability as being a criteria for consciousness and moving it down to the quantum domain where entanglement becomes a type of non-separability that can explain consciousness. I'm worried about certain consequences of this theory, especially once we take into account the fact that everything is entangled with everything else. There are many reasons for believing this. The Big Bang were conditions under which all things could be entangled with all other things. This is a consequence of many interpretations of quantum mechanics, like the many worlds interpretation of quantum mechanics. Everything's entangled, Bohmian mechanics. Even if you have a collapse mechanism, as in the case of Penrose, you still have something called Hegerfeld's theorem, which tells us that as soon as a particle is localized and unentangled, it will immediately spread out to infinity and entangle with everything else instantaneously. So we've got universal entanglement, which then seems to suggest that your theory implies the kind of universal consciousness that Deepak Chopra believes in, which might be a kind of reductor of the theory. So I take it you need some sort of, if you agree with me so far, you need some sort of, say, exclusion postulate, but then it looks like you're going to need some sort of comparison between classical non-separability and quantum non-separability to figure out how that's going to work. So do you have any thoughts on that?
Yeah, thanks. That's a very good question. I don't think I have a complete answer. So I think there are a lot of, a lot of things that one needs to think about here and calculate and go through carefully. And I'm not sure we have a full understanding of entanglement or non-separability just from the physics point of view yet to really draw full conclusions. But I think it's a fascinating area of research, both in physics and then, potentially with respect to consciousness. I think the only comment that I would have here is that, yes, everything might be entangled with everything to some extent, but I think the key question is by how much and what those differences are between different systems and subsystems, right? And so I'm thinking, for example, in physics, people do have metrics of entanglement. The most typical one is von Neumann entropy. There are other ones, and they're perfectly rational measures. They can be applied to systems, and you can get a number regarding how much components of that system are entangled with each other, and that number can differ by orders of magnitude depending on the situation. So maybe with consciousness, it's a similar thing where maybe you don't really have an absolute lack of separability ever, but you may have differences by many, many orders of magnitude, which could define boundaries and provide, some complexes with a lot of consciousness and others with very little. That's how I think about it, but I think it really remains to be seen.
Yes. Just to be clear, you would want to appeal to some sort of exclusion postulate, just like in IIT. You're going to perhaps agree that the whole universe satisfies the conditions for consciousness, except they are excluded by subsystems that have a greater level of entanglement, something like that.
Something like that, yeah. I'm not entirely sure what's the best way of formulating that. Is it really the exclusion principle like in IIT, or is it like, well, yeah, the whole universe is conscious, but subsystems within that universe are much more conscious, right? And you could have something like that. But yes, that's a good point.
Any more questions from the audience? How about questions among the panelists?
Thank you. So my question is for Matteo, right? Matteo, yes. So I'm curious, I think the examples that you were showing in your presentation, they had, they were pretty much purely feed-forward systems, right? And you showed how they would partition into this, well, not components, but assemblies of components, which were essential for understanding how the mechanism works. Just curious if you could comment on how that works in a system that's not feed-forward. Presumably it would be more complex, but maybe you have something more extensive to say.
Thank you for the question. Yes, so if it wasn't clear enough, the measure that I applied in the paper is not phi, it's not small phi, but it's alpha. And alpha is this measure that doesn't take into account the integration at the level of the system. It just takes into account the causal information of a determinate mechanism compared to the inputs and outputs. Alpha can be measured in integrated systems that have phi. So the actual causes that are measured by alpha are different from the intrinsic causes that IIT would say, because for instance, we just talked about exclusion. A system has a border, like you said. Actual causes can be outside of the system. I can find actual causes, for instance, of my visual cortex in my retina, actual causes of my retina in the environment, but I wouldn't find intrinsic causes at IIT because they have to be intrinsic, meaning within the system. So there is a correlation, though, between alpha and phi. Systems that have integrated information, they tend to have a high number of concepts in IIT 3.0 terminology, and every concept has a cause and has an effect, otherwise it's reducible. So there's a correlation between alpha and phi, meaning that if phi is high, alpha is probably high, but not the other way around. So you can have something that is absolutely extrinsic, it is not a main complex, but it does have causes and effects. And that's exactly the point of actual causation. It's extrinsic causation rather than intrinsic, a la IIT. Thanks for the question, though.
Yeah, that was a good answer too. Any more questions among the panelists? I have
a question for the last speaker. I've forgotten your name. Just from a philosophical point of view, do you think that it's absolutely necessary to have, in order to abstract a pattern, or, well, particularly to abstract a pattern like geometry, thinking of Platonic solids and so on and so forth, do you think it's absolutely necessary for there to be something implicit or intrinsic in our own makeup so that we're matching it? Or do you think we can identify patterns de novo without having any sort of Platonic basis?
I think that the way at which I am approaching it is that the brain has some way or another the concepts, the Platonic ideas, in the way of certain physical curvatures of space-time. So that is then independent or how we recognize it. And also this act of recognizing Platonic idea is, of course, then you make contact with that. And if it is so that they have specific, that a certain Platonic idea has a specific space-time form, then you make indeed contact with that space-time form without knowing it, because it works internally.
My question is it absolutely necessary to have the template there within us, as it were, in order to abstract? Is it necessary, or could we do it de novo?
I don't know, because I know, or anyway, the way at which I look at Platonic ideas is that you recognize them, but in this recognizing, there are an enormous amount of Platonic ideas also busy at that moment, active. So, but I think the physics itself, that if it is true, that is such that you have these.
I mean, a simple way of looking at it is we're made of the same stuff as the universe, with the same geometry in our atoms and molecules and our makeup. So there may be, you know, it's reasonable to say there's kind of some matching going on, which is a simplified version of your more complex description.
That's a nice way of telling it. Thank you.
No, I just wanted to make a quick comment, despite the fact the question wasn't addressed to me. But if in the paper that I mentioned, and if you take this whole business of the holographic correspondence further, something very interesting happens there. I'm talking about the correspondence between conformal quantum field theories and anti-de Sitter spaces. And what happens there is that you actually get geometry for free, meaning you actually get geometry from nothing, or not from nothing, but you can actually take a CFD surface with some really complicated quantum mechanics going on there, which is conformal. And then you can show that the dual actually undergoes geometrization, meaning you somehow get geometry by the fact that you're constructing space. And once you construct space, then it has certain geometrical properties, and these are very important to our most basic thinking. So there is a certain way in which you can actually get geometry de novo from science without, of course, you'd have to show that maybe if the neural correlates of consciousness would have such properties, for example, then, and there's a way of arguing that. If you're curious, I can send you the.
Yeah, thank you. Further questions, comments? I have a quick one for Amber, just out of total ignorance. It would seem that you could play around a lot with the coloration and intensity of the illusions that you present. Would there be any advantage to that, to make them a little more contrasty, a little darker here, a little lighter there?
Yeah, so in the case of the watercolor illusion, the one with the squigglies, the two layers of squigglies and the filling in of blue in the ring, that illusion has been used at many different contrasts and colors. And there seems to be a good ratio between the contours that is required for the maximal illusory effect. But yeah, there is an advantage of trying different things. We just went with blue because that was the most robust across people when we were piloting the experiment, but can be done with many colors.
Oh, okay. So you did base your images on a priori knowledge of what is like a 50% probability of people getting it right, or something like that?
We tried to maximize the illusion for initially. So we tried to configure the stimuli so that they were inducing as much filling in as possible. Yes.
Oh, okay.
Based on the literature, yeah.
Any further questions? Well, I think we can end our panel right on time. And I want to thank all of the speakers. You've done a really good job. And it's cleared up a lot of uncertainty that I've had in my mind. Thank you all.